Newton's method. So example number 4 gives us an equation. Oops, this is example number 4. Gives us an equation and it wants us to solve using Newton's method. Okay, so we are asked to solve the equation x to the third plus 3x plus 1 equals 0. All right. Now, clearly, we could go into the calculator and figure out what this answer is by graphing it and letting the calculator tell us what the zeros are. But did you know that your calculator actually uses Newton's method? And it's the same Newton, Sir Isaac Newton, right? Calculus was invented so that he could discover physics and do all the physics stuff. And he used this method to solve equations. So we're going to approximate a 0. Now, let me give you a graphic of how it works, okay? Let me give you a graphic of how it works. The way that it works is you calculate the tangent lines of a curve, and the zeros of the tangent line get closer and closer to the 0 of the actual curve, okay? And so let me show you how this works as soon as this pops up on the screen here. Let me turn off this. So if I graph this function, this is our function. I'm going to zoom in. What we're interested in is this little spot right here where it crosses the x-axis. Now, it looks like it crosses between 0 and 1. I'm going to zoom in on that. This is the x cubed plus 3x plus 1 equation on the screen, on the graph. I'm going to zoom in just a little bit to give you guys an idea of what this looks like. So I'm going to zoom in from, like, say, -2 to 1. Whoops. -2 to 1, and we'll just graph it from there. Now what I'm interested in is finding this 0. Where does it cross the x-axis? Okay? Now what Newton's method is he starts to approach and he looks for where it crosses the x-axis using linear approximations. So remember yesterday I said if you hit second program, it pulls up the draw menu and we can graph or draw the tangent line. So I'm gonna draw the tangent line, and I'm gonna come in from really far away here, and I'm gonna choose like some goofy decimal number just so you see what's going on. So if I draw the tangent line from there, okay, that's the tangent line. Notice that the 0, so we're interested in this. And the tangent line has a 0 of right here. Does that make sense? Now what happens is as I get closer, I'm going to draw another tangent line. So let's draw another tangent line. And I'm going to adjust the window. I'm going to adjust my window, the y values, because since we're dealing with 0, let's zoom in really close so you get a little bit better perspective of what we're trying to do here. So let's do -1 to 0, and let's do -2 to 2. So this is our function. Okay? And now I'm going to draw some of these tangent lines. So if I draw the tangent line now, there's one tangent line. Notice that it gets almost right, they almost have the same 0. Okay? Now if I come all the way to the right of that, so if I do this again, and I draw another tangent line, this time I'm going to do like -0.1. So I'm going to draw the tangent line at -0.1. What do you notice about the tangent line at -0.1?
It's almost right.
It's almost the same, right? So what if I were to do the tangent line at 0? So if I were to say, draw the tangent line at x equals 0.
Whoa.
So all these tangent lines for these x values they're all gonna be, as we get closer and closer to the zero of the curve, you'll see that all the tangent lines are gonna be very close to, their zeros will be very close to the original function's solution or zero, okay? You guys see that? So now Newton's method is if I want to solve the zeros for this, I'm going to go through this process where I'm going to find an x value. Let me write this down. Like that. Now what this is saying is I'm going to arbitrarily choose any x value. Okay? And if I plug in that x value into this formula, it will give me another x value. And then it'll give me another x value, and another x value, and another x value, until we get very close to the x value, which is the solution of the function, based on the graph. Does that make sense? So what I'm going to do then, what does this look like, Mr. Adams? Well, the way this works is I'm going to arbitrarily choose an x value. Now your textbook recommended 0.3, negative 0.3. Actually, that looks a little sloppy. Let's be a little more formal. 0.3. Now that's my first term. Now what that means is that my next term, x sub 2, would be equal to x sub 1 minus f of x sub 1 all over f prime of x sub 1. You say, well, Mr. Adams, I don't quite understand the subset notation. I don't feel real comfortable with that. Well, get used to it. I need to know what the next x value is. Now what this does is I'm guessing, this is a guess as to what the zero takes place at. In other words, the zero of the original curve, I'm thinking might be 0.3 or negative 0.3. By using Newton's method, I will hone in and zero in on what it actually is. So now what I'm going to do is I'm going to go through this process a series of times until my x values are very close. Does that make sense? So now this would be negative 0.3 minus, and the original function was negative 0.3 raised to the third power plus 3 times x, which was negative 0.3 plus 1. Right? That was the original function. That was f of x, right? You remember that from the last slide? Now what would f prime be? Let's go back and look and see. If this is f of x, right? If this is f of x, what would f prime be? Well, f prime would be 3x squared plus 3, wouldn't it? Is that right? So if I come back here, I'm going to say 3 x prime, which is negative 0.3 squared, or x, plus 3. Is that right?
Yeah.
Yes.
Yes. Now, to crank through this, and get the answer, all right, here we go. You guys ready? This gets a little tedious. I'm going to cheat a little bit. If you notice, I've got the 0.3, 0.3, 0.3, which represents x sub 1. One way that I could cheat, I don't want to plug in negative 0.3, negative 0.3, negative 0.3. So one way to cheat on the calculator, and it's not really cheating, I shouldn't use that word, but to make my life simpler, I'm going to come in here, and I'm going to say 0.3 is my x value. Now what that does is it takes the variable x and assigns it a numerical value, so that whenever I enter in x, it's the same as entering in negative 0.3. Makes my life easier. So the arrow is this store button here. See this button that says store?
Oh.
Okay, I'll give you a second to figure that out.
We need to do like a calculator day. Just teach us all the cool tricks.
I am, right now. Where's your calculator? Get it out and practice it. Maybe you'll remember the tricks that I teach you. Alright, so now what I could do is the formula was x minus, right? Then in parentheses, this is the numerator, it was x cubed, right? Plus 3 times x plus 1. That was the numerator, divided by the derivative. The derivative was 3x squared plus 3. And so right now what your calculator is going to do for us is that whatever we plug in, when I hit enter, wherever there's an x, it's going to automatically plug in negative 0.3. Okay? So now I'm going to hit enter. And I get negative 3.2232. Okay? So let's write this down. I'm going to keep a separate list. X sub 1 was equal to negative 0.3. X sub 2 was equal to negative 0.322. 32. Now x sub 3 would be what? X sub 3 would be the exact same thing, except instead of plugging in 0.3, what would I plug in?
0.32.
Yeah, the next number, right? So now I'm going to cheat a little bit, and I'm going to say negative 0.322324159. Store that as x. Hit enter. Now what do I type?
Hit second.
Second entry?
Yeah, and just bring the other equation back up.
Hit it again. No, like second enter, second enter, second enter, second enter. No.
I'm doing it. If
Yeah,
I hit
no, but you
second
have to get
entry,
it back to the last
Second
equation.
entry.
Again. Again. Do it again. Wait, don't
Gotta
put it
keep
again.
it until
Yeah,
you
do
get
it.
back to the original equation.
One more time. Yeah. Ah. Wait, what are you doing, bro? Yeah, do it.
It's
really confusing that way.
Wait, okay, let me do it.
okay, you do it real quick. There it is. Oh, you had it. All right. Well, I'm going to show you. I see what you guys are trying to do. That was good. I'm going to show you a quicker, easier way. Okay, you guys ready?
No.
Okay, here we go. You ready? I'll edit it out, Joe. If I say x minus in parentheses, well, clearly there. Hey, you know what? I got a good idea. You guys want to see the shortcut? Let's just show you the shortcut because I don't feel like entering it in. Why don't we do this? You ready? Get your calculators out. Here we go. I'm going to put in there for y sub 1 the original equation, and for y sub 2 I'm going to enter in the derivative. You guys with me?
That seems a lot longer than a shortcut.
Really?
Hit second enter a couple
Really?
times.
Here we go. So now that I've done that, let me show you a little nifty trick. We originally said that negative 0.3 was going to be our original x value. All right, cool. And the process, what we did was, weren't we doing this? Weren't we saying x minus our original equation? But what is our original equation now?
Y1.
y1. So if I hit vars y1, I'm going to take y1 and divide it by what?
Y2.
Y2.
y2. I'm going to hit vars function, choose y2, and now we take that value and we store it as x.
Enter.
Hit enter. Oh, hey, that was good. Hit enter. Oh, hey, that's the next term. Hit enter. Next term, next term, next term. What? I teach calculus.
It's the same.
It's the same, but it's quicker and easier, right?
So
Now, what do you notice about the numbers, though?
They're all this.
really close.
The last three are the same.
The last three are the same. That's how you'll know what the zero is that after so many terms, the numbers seem to be the same. Now, the truth is, if you go over like 12, 15 decimals, it's a little different. right? But we don't need to be that precise. So what am I saying? Well, what I've done is on my calculator, I have gone and I've calculated that this is x sub 2. X sub 3 was the number after my 3, 2, 2. So x sub 3 was this number here. That's x sub 3. X sub 4 is this number here. X sub 5 is this number here, and x sub 6 is this number here. Okay? And so what we see is right after x sub 3, it gets pretty close to the same. So x sub 3 is 32218, negative 0.32218. And then if we were to approximate x sub 4, it would be negative 0.32218. And there's a 5 and some other things. What do you think the 0 for that function is?
Negative.
That number, right? So how do we find that? Well, let's see. If I come back to the original graph, and I'm going to change some things now, so I'm going to clear my drawing. So if I go to draw, I can clear the draw by choosing option number 1, and that'll erase all of my tangent lines that I've drawn. And then I'm going to set my window to a standard fit, which is 6. And then the other thing that I want to do is I turned off, notice that Mr. Adams turned off my derivative, because I don't want to graph that. I just want to look at the original function. So what I've done is I'm just going to graph the original function on my calculator. And I can find the 0, and I let the calculator find it, and it should be what number? Negative 32218, right? Or something close to that. So if I hit second trace, I get the calculate menu. I want to find the 0, which is option number 2. My left boundary, I choose that. My right boundary, I choose this, and I get somewhere in between, which I can't. And then I let, hey, look what it is. Negative 0.322.
20.
Right? Does that make sense?
Yep.
Yes.
So that's
Any questions? Yes.
Is this the graph of the original?
The original equation x cubed plus 3x plus 1. Our goal was to solve it. And so I'm glad that you said that. So what did we just do? Well, we used Newton's method to solve this. And so what does that mean? That means that x approximately negative 0.32218 is a 0 or a solution to f of x, which is x cubed plus 3x plus 1.